Hello and welcome back. So in this video, we are going to be looking at a so-called active shape models. Again, a very powerful tool for image segmentation. Okay. So far, we have looked at models, segmentation models that depend on the strength of gradients to localize objects of interest in the images, or for instance, organ segmentation in the case of medical images. Okay. So, if you consider both active contours as well as geodesic active contours, the classical snakes and the geodesic active contours, even in the level set formulation, the localization is done mostly on the based mostly on the fact that the edges of the objects of interest have high gradients. Okay, so in order to regularize this problem, we had smoothness terms, so that the contour doesn't get too wiggly or too oscillatory. Okay, however, what we didn't have is an idea of the shape of the object. So there are no image priors that we have incorporated into these methods, correct? So we are only looking at, okay, the contour should be smooth and ideally it should be on the edges of the organ of interest, primarily because that's where the gradient strength is very high. Okay, but it would be nice if we can incorporate some knowledge that we already know from prior knowledge in order to help the segmentation. Okay, so the idea behind this active shape model is to incorporate some form of image prior, in the sense exploit the fact that we do have some idea about what the object looks like. Okay, and how is that possible? Here first we are going to run into this so-called training data, wherein we have a collection of images which contain the object. Now that object might not have the same pose, orientation or size. They might have different scaling factors, but they are all the same object. And from those training sets of images, the idea is to construct a model, a shape model, or so-called statistical shape model, which we can then use as a template. Now, why would we need this? We can just create a template, like a toy template that we typically do. Now, here's a difficulty there. So, for instance, let's say you have like car number plates, right? If you have number plates in a car, so you can have things like this, this box. This is a typical number plate with TN07, some number, right? So then you can localize. Now if you're going to look for number plates in a car, or for instance signboards in, as you're driving around, right? Let's say you have a signboard, something like this, okay, etc. So then you can always construct a template, which has this shape. Pardon me for a second. So this has something like this, right? Some shape, and then you can have some identification here. Similarly, for this you can construct some template. So this is our template that you can construct, right? And then once you are given an image to look for this, you can just scan for this template by doing a cross correlation. And wherever there is high cross correlation, that's where you do the localization. However, this works only if the objects are of fixed size and orientation, and these are mostly very rigid objects. Okay. Now, in many cases where we are going to do image segmentation, we are looking for slightly more flexible objects, right? Where, for instance, face detection, not all faces look the same. They are all of slightly different shapes and sizes. So we should be able to, take that into account, correct? So that's another thing that we have to worry about. So in the event where, there is a huge variability. When I say huge variability, within the limits of, what we can, may model. So we can't have like very amorphous shapes, etc. But for instance, like I said, face is a good example. Organs are good examples of shapes which have some variability, and we can't use a fixed template. Now, in those cases, what we are looking for is a model that encapsulates the range of shapes that are possible. Okay, range of shapes and deformations that are possible on a basic shape, and that model, if you have, then somehow we use that model to find out where that object is in the picture in terms of the shape parameters, and then eventually achieve the segmentation or localization. So that's the idea. That's the general idea behind the active shape model paradigm. Okay, so let's get into the process right away. The first step is to build the statistical shape model. Okay. Now, how do we go about building this so-called shape model, right? So first we need a set of training images. That's absolutely required. When I say training set, or you can say example set. In this case, I wouldn't really call it training set. And I'm borrowing phraseology from machine learning literature, but we should call them example images, right? A bunch of example images where we have ideally have cropped out the object of interest. Okay, and of course, needless to say, they of course contain the object of interest, but where we also zoomed in and cropped it out, let's say, right? And the images are annotated by experts. Here, the annotation is twofold. One is like, of course, we have localized the object. Second, in the picture and crop it out. And the second is to select a bunch of landmarks, control points, if you want to call them, that can be used to represent the shape. Okay, and these control points or landmarks should be found in all the shapes. Shape instances in the database. There is a spelling error here. Delete that. Okay. So then, what are the good landmarks? How do you decide what these landmarks are? Again, basically they depend on the shape, correct? And with whether these are sharp corners, high curvature regions. Sometimes you just put equally shaped points on the boundaries of the shape. So let's just look at, typically I'm going to just draw some a boundary of a shape and just tell you what, how we can annotate them. So for instance, if you have something that goes like this, you have a, sharp point here, okay, and then maybe something of this sort, okay, and, you have this extending, okay. Let's say this is some shape, the boundary of some shape. It doesn't matter what it is. So then for annotation, we might have to choose these points, correct? These points, okay. And maybe because here, we want to make sure that there's a connection, we can just choose some intermediate connection points, etc. Okay. An easier example is if you have a face, something like this, you have somebody's face and maybe wearing a hat, there's eyes. Okay, then you might have to do landmarks. The landmarks will be something like, let's say here, there, maybe you can have some points here, the tip of the nose, maybe some points there, be some near the temple region. So if you have an ear, right? I haven't put in the ears here, so somebody who has some, decent ears, kind of not very human, but still, edges of these ears, etc. So that will give you a nice template, right? A bunch of points that tells you. Then you can also do something around the face. So this gives you the control points that describe a shape, right? So first you need to have this annotation done so that you can have for every shape all these points should be present. So that so that for instance in our case, let's say for this in this lecture we're going to consider like to say n points per shape, right? So basically points are the form x1, y1, so on and so forth to x and yn. Okay. So so that, but then all shapes in your database that you have your so-called example data or training data, for every point in the training data you need to, for every shape in the training data, or you need to have n points annotated on them, and they should all correspond to the same landmark. So that's the idea. Okay, so like we saw, the shape is represented by the points and is arranged as coordinate pairs. So for 2D objects, it's what we are going to talk about in this lecture. We can use in this kind of an ordered pair approach, x1, y1, x2, y2 up to xn, yn to represent the shape. And we typically use small n as the number of landmark points, or for the sake of analysis, we'll typically write this down as to an element vector, that is x1 to xn and y1 to yn. Okay, and of course, like I said, all instances in the training database, once again you can call it an example data, should be described using the same number of points. So make sure that the landmark points are present in all instances of the shape in your database. So that's very important. So once you have this, once you have this ordered pairs, let's say you have S data points and you have 2n for every every shape you have 2n element vector. Okay, then next we move on to how we build this so-called statistical model. Okay, so the first algorithm here, the first step here is we have to, once we collect the set of points, right? So for every shape we have, so here once again I'm going to be abusing notation here a bit. So ideally we need to have two indices, one to index the points in a shape, and the other one to index the instance of the shape. But depending on the context, I hope that you will understand, but I will also make it a point to explain. Okay. So we collect all the the points corresponding to all the instances of the shape. So let's say there are data points in our training data set or example data set. Then first step we have to do is to align the shapes. Okay. Why is an alignment required? Because these shapes may be in arbitrary orientations or pose and magnification, that is scaling in the training data set. So we don't want that, right? So what we want is a variation of the shape, but we don't want to have them in different poses. Okay. So the idea is we can always estimate the pose and the scaling. What is hard to estimate is the natural variability of the shape. So we want our model to encapsulate just the variability of the shape itself and not its pose and magnification or scaling. Okay. And that's the one step that we have to do. Okay. So this is the first algorithm. Once we have a model, statistical model, then it is best to reduce the dimensionality of the model. So what do I mean by reducing the dimensionality of the model? Okay. So here, think about it. So you have a shape which has n data points, right? So which is basically 2n numbers are used to describe that shape. N data points, each point is an x comma y, correct? So, but if you want to, let's say, modify the shape a little bit, right? Say you want to deform it a bit, then we have to work on all these n points, right? So or 2n numbers have to be changed. And of course we have to, and even if you want to make minor mod, let's say even if you change 1 point at a time, maybe you will not be able to express yourself well. So you might have to change a bunch of points at the same time. Okay. So to make this job easier, we have to do this dimensionality reduction so that we have a very few numbers that we can fiddle with. You can call them shape parameters, so that changing one of the numbers will lead to some tunable shape transformation. Okay, so we will see that later on. But the idea is, again, if you understand this, basically you have a lot of xy coordinates describing your shape, and if you want to change the shape or deform the shape a bit, then we have to change all the n xy coordinates. Instead, if you reduce the dimensionality of the data, then we don't have to change so many numbers, but change only a few numbers to get the kind of shape deformations we want. Okay, so the first step in aligning shapes is to translate each shape so that its center of gravity is at 0, 0. So basically the way to do that is to estimate the centroid by just calculating, let's say, x bar and y bar for each shape, which is nothing but, so x bar would be the average of all the x coordinates by total number of points, right? So x1 plus x2 plus up to xn by n. We can write this better. 1 second. So this is x bar and y bar are calculated so that x bar and y bar are calculated as the mean of the x coordinates and mean of the y coordinates, and then you subtract that out from the individual coordinates. The second step is to choose one of the training shapes as a mean shape and scale its coordinates so that if you calculate its length, it's unity. So basically what we want is the square root of this is for a particular shape. We can do something like square root of x1 square plus x2 square plus so on up to, there are n points, xn square is equal to 1. Okay. So you want to do a normalization like that. So what we are doing here is kind of scaling the shape, right? So take the scale factor out. Okay. And the last step is to align all the shapes to this mean shape. Okay. And this alignment is done by estimating a scaling factor and a rotation matrix. Okay, and this alignment actually we can pose in the form of an optimization problem. So let's look at how we can align two shapes. Okay, and then all you have to do is we have apply this to all the shapes in the database, and choose one of the shapes as a mean shape and align all the other shapes to it. Okay, and then we'll just look at how we can do two shapes at a time. Okay, so the idea is we have the two shapes which are centered at the origin. Okay, that much certain, and we wish to scale one of the shapes, let's say x1, by s, and then also rotate it by angle theta so as to minimize the loss function. So let's just write this down. So we have two shapes x1 and x2. Okay, two shapes x1 and x2, and we want to scale and rotate. Scale and rotate x1 by s comma theta. So small s theta. Okay, and the idea is to and how do we estimate this s and theta? It's by minimizing this loss function s a x1 minus x2 squared. Okay, so a is the rotation matrix. Okay, that much is done. Okay, so it turns out then the solution to this optimization, if you solve this optimization problem by basically what we have to do is minimize this loss function with respect to these parameters that we want to estimate, and we'll end up with the following formula. Okay, so A is use a different color. So A is given by small a is given by x1 dot x2 divided modulus of x squared, and there is a b which is given by summation I equal to 1 to n x1 I y2 I minus y1 I x2 I. This is divided by modulus of x1 squared. Okay. So if you look at this formula, we have both this factor a and b. Here the i's refer to the coordinates of the individual points for shape x1 and shapes x2. So when I say y2 refers to shape 2, the y coordinates of shape 2, and I is the specific y coordinate of, let's say, landmark point I. Okay, so that's how you have to interpret it. So the i's actually subscript the individual points in a particular shape. Okay, so if we estimate this a and b from here on, it's the scaling factor is on top of this estimated as, if you want to use a different color, then s square. This is given by a square plus b square, and the rotation angle is arctan or tan inverse b by a. Okay, so if you have two shapes x1 and x2, and if you want to bring x1 in alignment with x2, then you have to scale x1 by this s and rotate by theta. So all of this is, of course, when I say scale the shape, etc., what we are trying to do is to apply these transformations to the coordinates which describe the shape. Now we know how to do that because we have seen some of this in our image registration. So this is something like image registration, but we are only considering a specific set of transformations, and this typically applies to situations where we have a bunch of points describing a shape, and this is often used. This is referred to as Procrustes analysis. Okay. So once again, to reiterate, why do we need to do this? It's because when we are annotating our training database with these landmark points, so all the points in all the data in our training database, so let's say images basically, will have the object that we want, but they will all be in different poses and scales. We are not looking to estimate, we don't want to have a distribution over all possible poses. That's impossible. but or scaling factors for us. That's what we want again is to capture the natural variation in the shape of the object that we are trying to segment or localize in the object. So this is the first step. So once we have annotated, then we take those points and bring them all into a common coordinate system. That's precisely what this is doing. So that now we have for every control point, they're all in alignment. All the corresponding control points in every shape that we have annotated is in alignment now. Okay, so that is what you would refer to as a point distribution model. The second step now, the second algorithm that's used is the principal component analysis. Now that we have all the shapes in a common coordinate system, what we want to do is to reduce the dimensionality of the data. Now we only know that every shape is represented by n points, and then if you want to deform the shape in any way, we have to deform all the n points. That becomes a little bit hard. Okay, so it'd be nice if we know the variations in the shape that can be controlled by a few parameters. So by varying those parameters, we can control the shape very effectively. Okay. So, and this is accomplished by using something called the principal component analysis. This is a technique. In fact, this should qualify as one of a most older machine learning technique. And this is typically used to remove correlation between features in data. Okay. So the other way of putting it is it's used to diagonalize diagonalize the covariance matrix of the data. So when you diagonalize the covariance matrix of the data, what you do is you will remove the correlation between the features in the data. Okay. So and in the process, what happens is that you will estimate a new set of axes for your data, and you can also interpret the process of principal component analysis as the rotation and translation of your or translation followed by rotation of your coordinate system that you are into another coordinate system, so that the correlation between the features are removed. Okay, so we'll look at an example in the next slide so that to understand this particular scheme better. Okay, so for instance, let's look at this data here, which is plotted. This is a toy plot. So I'm going to call this just to not confuse people. Let's say there are two features. So I'm going to call them F1 and F2. Okay. So these are so many data points. Each data point has two components, F1, another component is F2. Now we see that there is correlation between F1 and F2, right? So we can draw this correlation. Let's say I'll use red. Let's say something like this, right? So this line kind of captures this correlation between F1 and F2, right? Because if you know F1, you can kind of estimate F2. So that's what this means. So, but if we actually have a line like this that goes through, I'm just hand drawn this is very crude, that goes in this direction, and then you have another line, let's say, which again in this case it's not drawn properly, but let me redraw this so that let's make this clear. So I'm going to indicate with a very large blue thing. Let's say this is the mean, right? This is the mean of your data. Mean of this point is F1 bar, F2 bar. Okay. So I'm going to draw a line that goes through that. Okay. Another line that goes through this. Okay. So we're going to call this F1 prime, F2 prime. Okay. So this F1 prime, F2 prime is a new coordinate system. Okay. And if you see what it does, what it has done is that this F1 prime, right? F1 prime captures the maximum variance in your data set. Okay. So because there's a lot of variability in the data across, if you go along the F1 prime axis, while the variability along the F2 prime axis is very low. Okay. So now if you look, this also is a translation and rotation. So because we have drawn the axis through the centroid of the data set, so to speak, we have calculated the F1 bar, F2 bar, and that's the centroid of the data set, and we have drawn our axis through that. So it's a translation wherein we have subtracted out the mean from each of the data and then the rotation of this axis. Okay. So if we do this transformation, then we see that we can actually describe our data with just f1 prime. Okay, because the variability across f2 prime is so low, we just need f1 prime to tell where the data is. So for instance, if you want to, let's just look at this particular, let's say some data here, I will draw separately. Let's say there's a data point here, right? And if you want to describe that data point, then all we need is some projection of this data point onto f1 prime axis. This projection here, and they're using this point from the origin. What is this distance? We can describe this green point. Okay. So instead, but then previously to describe this green point, we needed both f1 and f2. Now with the new coordinate system where you are translated and rotated, we just need f1 prime. Okay. So we have reduced from dimensionality of 2 to dimensionality of 1. Okay, this is precisely what a PCA does. Another thing it has done is to decorrelate, in the sense f1 prime is not correlated to f2 prime at all. Okay, in the first case f1 and f2 are correlated, but now f1 prime and f2 prime are not correlated at all. In fact, it has figured out the axis, so that I've drawn the axis so that maximum variance is along f1 prime axis. f2 prime axis has very little variance. Okay. So this is what in general a PCA accomplishes. What it does is, if you have a coordinate system, the coordinate system once again need not be spatial. In our case, it's a spatial coordinate system, right? We have a point cloud. We have a bunch of points describing a shape, right? And we have a point cloud describing a shape. And what we want to do is to reduce the number of points that describe our shape. So in general terms, we have a bunch of features describing our data. And it'd be nice if we can reduce the number of features used to describe our data by removing the correlation between the data. Okay, so that we only keep the features or the directions which have maximum variance, and we can actually ignore directions where the variance is low because it doesn't add any information, any new information. Okay, so this is the function of PCA, and we are going to do this for our shape model. Remember, our shape model is nothing but, our statistical shape model is nothing but collection of x comma y coordinate pairs drawn from different instances of the shape that we are trying to describe. Okay, so for every landmark point there are a bunch of x comma y coordinates. So since we have that, how do we now reduce those? Let's say we have n points, right? 2n numbers, actually n points, 2n numbers. Can we reduce this to a smaller number of parameters that can be used to control the shape? And that's exactly what PCA accomplishes. Okay, so now we are going to see how we are going to actually calculate this, the eigenvalues and eigenvectors. So I'm just going to walk you through the PCA calculation steps, very briefly. I urge you to again look up some text. There are lots of videos online that you can consult to understand this actual computation. So the first step is to compute the mean of the data. Okay, so we have to subtract the mean out for this to make sense. The reason is because we are trying to look at oscillations around the mean, right? Not the absolute values. So we calculate this x bar as, if you sum over. So once again, there is some abuse of notation s we used for scaling factor also. So I'm just going to use a slightly maybe a larger s maybe to see I equal to 1 to s. This is the mean of the coordinates. Then again, if you compute the covariance of the data, so covariance of the data, I'm going to call it C. It's 1 over s minus 1 summation I equal to 1 to s, large s, and you have xi minus x bar times xi plus x bar transpose. Okay. So now the third step is to compute the eigenvalues Pi and the eigenvectors lambda I of C matrix. Okay. So this is the calculation that you have to do. So once you have this C matrix, this is the covariance matrix of your data. Like I said, the idea behind the calculation of the PCA is to make sure you diagonalize your covariance matrix. So then you're trying to actually estimate axes which will make sure the data doesn't appear correlated. Okay, so that each of the axes are uncorrelated. Now the next step, once you have the eigenvalues and eigenvectors, the idea is that each of the eigenvalues tells you the variance of the data about that axis, right? About that axis from the mean, about the mean, right? So that's why we subtracted the mean out. Otherwise, the computation won't make sense. So we subtract the mean out, and we only have this variation in the data from the mean, and that's what the eigenvalue gives. So you can calculate the total variance. So the fourth step is total variance Vt is the summation of all your eigenvalues. Okay, and ideally we want to choose the t largest eigenvalue. So in the example I showed you, I just it was in 2 dimensions. We had f1 and f2, and then we did f1 prime and f2 prime. So that f2 prime had very small oscillations and it was uncorrelated f1 prime. So we ignored it, we threw it away because the variance there was very little. So we do something similar. If there are more dimensions, we choose. But now what is the criteria? Right? We choose the t largest. Choose t largest eigenvalues which capture, let's say, a very large percentage of the variance. Okay, so the way you would write it down is you would say summation I equal to 1 to t lambda I is greater than some fraction of the variance. So this you would set it as, let's say, 0.9, 0.95, 0.98, depending on what gives you good accuracy. Typically, let's say 98% is what is used. Okay, even at that high threshold, you will lose a lot of the axis when it's not necessary. Okay. Now, once you have this, what is the point? As I said, we saw that, right? When we did the 2D example, we saw that once we have the f1 prime, f2 prime axis, we are able to express every point just in terms of the f1 prime axis by taking a projection of any arbitrary point onto the f1 prime axis. So that's pretty much what you are going to do is we are going to project every x onto the t axis that we have left. Okay, so and that once we have projected them, that gives you the sets of coordinates. We call them B. That can be used as shape parameters. Okay, so the idea is that we can approximate any training set data x as approximate as the mean plus p times b. What do these mean? The p is nothing but this particular matrix where each column is an eigenvector, but it has only t number of columns. Okay, so it has t eigenvectors, and b is a t dimensional vector. So b is just, like I said, b is very similar to that f1 prime we saw. Okay, when 2D it was easy to see, but in more dimensions it's much harder to see, right? So b is a t dimensional vector and b is a t dimensional vector. Okay. And how did we get b? In that case, in the example case, we got this f1 prime by projecting an arbitrary point onto the f1 prime axis. So similarly, we would have to project any arbitrary x onto the t axis, and that is done by the following expression: P transpose x minus x bar. Of course, this is done after subtracting out the mean. Okay, so if you see this will be consistent dimensionally. This is a good exercise. I won't do it now, but I would urge for you to look at what will be the dimensions for each of them. Make sure that they are dimensionally consistent. Okay, make sure it's meaningful. Okay, so the eigenvectors, what these t eigenvectors represent is a rotated coordinate system. Okay. And the parameters b or the new points, those are the models. So if you change b, you can change in the models. So they are the most significant coordinates of the shapes in this rotated frame. Okay. So this is the purpose behind doing the PCA, because now we have this ways to you can look at each one of these b's as some kind of button that you can press up or down on, and so that you can change it. If by changing its value, you will change an aspect of the shape. Okay, so let's understand this slightly better. We have looked at the f1 f2 prime example, but we can also just to reinforce this, we'll look at it one more time. Okay, so let's consider this picture, right? So for instance, this was our original point cloud distribution, and we had constructed the new axis, right? This is our p eigenvectors, this is our p. Okay, so any arbitrary point, if you look, let's say this is an arbitrary point that we want to project, let's say some x. Okay, this we can project to here, to x prime. All right, and what is b? B is nothing but the distance along this axis. That's the coordinate of that point in the new axis. So this is this distance. This distance I have indicated here, right? That's your b. So in your new system of coordinates, and what are your what is your coordinate values? That's exactly what this does. Okay, so it's a very in 2D it's hard to understand. Of course, when you go to higher dimensions, it's not easy to visualize. But this is exactly what it's doing. So in the problem, if you look at it from the point of view of diagonalizing the correlation matrix, if you think of it this way, if you look at this situation, there is correlation between these two data sets, right? Because you can always draw a straight line, and you can use that to predict one from the other. Okay, so that is possibility. But here, if you look, since our axis is aligned along the maximum variance, if you take this axis right here, this axis passing through the origin, through the mean of the points, this is uncorrelated with this axis. Okay, and the variance along this axis is much lower compared to variance along this axis. So we, in the sense, when I say this axis, this horizontal axis right here is where the maximum variance is, and we can safely ignore the other axis, right, without losing too much information. So that's the idea behind doing the PCA. So now we have done two things. We annotated the training data with control points. We have aligned all the annotated training data to a common coordinate system, and then we have done PCA to reduce the dimensionality of data, so that we can now describe the shapes using a fixed set of parameters. Call them B. We call them the shape parameters. Now, how do we use this to identify objects in a new test image? That's what we are going to see in the next few slides. Okay, just to recap a bit, there's a couple of points that I would like to reiterate here. So now we have the shape parameters B, okay, corresponding to each of the axes, that new axis that we have estimated from the PCA. Now we know that the lambda I, which are the eigen values corresponding to each of those new eigenvectors or the coordinates, they describe the variance along that axis. So what this PCA also gives you is this parameter 3 times square root of lambda I, which I'll write this here, 3 times square root lambda I for every bi corresponding to an eigenvector. We can actually estimate the 3 times square root of lambda I as some kind of a, this is actually 3 times standard deviation, if you think of it that way, so that we know how much bi can vary. So that gives you some limit. So you can't arbitrarily vary bi, so you make sure that you always vary bi within these limits. Okay, so that's a good way to actually adjust shape. So this also tells you a drawback or the constraint of the method, because this 3 square root of lambda I comes from the original data, which is our x and y coordinates, right? So what it means is that you cannot have shapes that are too different or outside the bounds described by your training data. Okay, so if you have like an extreme version of your shape, whatever that, however you qualify extreme, then it's not going to be, this method will not work. So that's, but another way of looking at it is that it gives you a very systematic way of imposing constraints on bi. Okay, now you know its maximum, this 3 sigma is here. So now you know how much, what kind of constraint to put on bi, because at some point we'll be estimating the bi's, because that's what tells you what the shape is. And we want to make sure that it won't go beyond these limits. Okay, the last piece, or should I say the penultimate piece, is to match the model to a target in test image. Okay, so first let's just look at this problem as how would you match a model to a set of target points in the test image. Now we assume that target points are given. Okay, we'll see how to get those target points later. First, we'll see that there is a bunch of target points that you have somehow figured out in the image, which hopefully will correspond to the shape that you are looking for. And what you want to do is take your model. Your model is now described, remember, by B. You want to do some rotations and translations on your B, so that the shape that you have, that model that you are working with, matches the Y in the data. So basically, you are trying to solve this optimization problem. Okay, the way to solve this optimization problem is the following. Is basically you take a shape parameter, initialize your shape parameters by setting B equal to 0. So that is, you will start off with the mean shape. Okay, and you generate the model point position using this expression. Okay, you have the P axis. Now we do this. Now find a scaling rotational transform which will align X to the target points Y. Okay, so you'll do scaling, rotation, and also translations. Okay, all three of them. I think I left out translations here. Please add them. So this is a sum of this would be a rigid body transformation that you're looking at, but you're doing it to a point cloud rather than to objects. Okay, so find this rigid body transformation that will align X to Y. Okay, so once you have estimated it, you would want to project this back into the model space. Now you have taken your model B. B is your shape model. Now you have projected it into X space here. Put it back in the image. Now aligned it with the target points Y, using and that you do by doing some transformation, estimating a transformation, and then you take that transformation, apply it to your Y point, so that you are now putting this into the model space. So in the model space, now you estimate B. Okay, and this B describes your shape. Okay, if this and you repeat this till convergence. Okay, repeat from step 3. So you have to start from here. So for this B, generate a new shape and then put it back in the picture. Estimate a transformation which will align the shape with the target points. And you keep doing this again and again, so till you converge. Okay, so that way now what you have done is you have taken your model shape and arrived at another shape which is similar to what is there in the picture that has been given to you. Okay, so now we can take that model parameters and now we have a description of the object in the test image in terms of the B's. Okay, so that's the power of this technique. Okay, so now the question I'm sure in your mind would be, what is this Y? How do you get this Y? So because intuitively, what are you expecting, right? What do you want to do? So just draw this so that we all on the same page. So ideally, you have this picture, right? Big picture, let's say a bunch of some birds flying, something, and there's a cloud, etc. And then there's a guy standing there with a face. Let's just draw his face. So you have this guy here, right? So die we drew earlier. Okay. We has a different year, right? And this is the guy, and we want to we have our shape model. We saw that we did our shape model. So let's say our shape model looks something like based on this B, we have now projected. Now let's say our shape model looks like this. Okay. This is our shape model, right? Looks more like a monkey, but it's okay. Maybe this is our shape model. And now we want to align this to here by estimating a rotation and translation. Okay. That's what we do. So we would align this. Now, how do we know where this is? Right? We don't know. We wouldn't know where this red face is in the picture. Where would we put this guy? So that we can estimate rotations and translations and scaling. Okay, so this is very similar to image registration, except that now, like I said, we are trying to align a point cloud to another set of control points. So this set of control points here are estimated by or given by Y, and we want to know how to get that Y. Okay, so that's the next step. So then, how do we estimate Y? Where in the picture is the object? We don't know, because if we know the object is in some location in the picture, then we will take our B's, transform it into image space and initialize it somewhere close by, so that it's easy to estimate the rotations, translations and scaling. Okay, but we will not know that, right? Because we won't even be able to see that. In a semi-automatic way we can probably know, but otherwise we won't know. So first we initialize the model in the image space. Then for every landmark point in X, we search along a line, normal, not tangent, sorry. We search along a line which is normal, and for that it's basically you draw a tangent, you search along normal. Okay, search along normal. There's an error in the way I wrote it, so please take that into account. So then for every landmark point, we search along a normal to that point for a high gradient point, assuming that the edges have high gradient. Okay, so this is again, we are still once again back to using gradient, right, which is like a bad thing which you want to avoid, but there's no other good marker right now. So we look for, so let's draw this in the next page, so that next slide, so that you know what I'm talking about. So for every landmark point you draw a normal to that point. What do you mean by normal? The normal is defined by it being 90 degrees to the tangent at that point, and we again, once again, how do you do the tangent? We assume that the shape model can be seen as a boundary of an object, so it's like a curve, so we can have a tangent at every point, and to the tangent we draw a normal. Okay, so you search along the normal till you hit a high gradient pixel, and that's your y. Okay, there is another approach which is again slightly more sophisticated than this. So now we have this shape model. We can also do the so-called appearance model. So let's, for every landmark point in the neighborhood of the point, so you draw a small line which is again normal to the tangent at that point. You take a line and you look at the pixel profiles there. Okay, and then you can construct a statistical model of the profiles around the control points. This here, when I say the profiles, I am talking about the intensity profiles. So I will look at the pictures in the next slide. So if we have intensity profiles around every landmark point, and you search again along the normal till the intensity profiles match. So that's another way. Instead of just looking for, let's say, a strong gradient, you can look for similar distribution of pixel intensity values in and around a control point. So that much we can do. Okay, so once we hit, then we get this y. So we can now have a bunch of y's, or the y that we, or capital Y as we call it, which describes a bunch of points, which is most probably the shape that we are looking for. Okay, so once again, so let me just draw this so that we know what you're talking about. Let's say we have, this is a picture, this is our image, right? So let's say there is an object in there. Use red. There's some object in there, right? It's the object. Okay, this object we are looking for possibly, and then we have a shape model. Shape model is like this. We'll draw this, and these are our control points. So from B we have got this. Okay, let me once again. Okay, so the idea is now to let's say we put one more point here. So the idea is now to look at, let's say there's a tangent here, and then we look at the normal along this direction. So you search along this direction. You can search on both sides. Typically, either way is fine. So you would go along until you hit, let's say this is a high gradient point. Okay, now you mark this as some yi. Okay, you do that for every control point. From here you draw some normal, similarly from here, so that you have an idea that from every point on your model curve, you draw a normal and then you search along that normal. That gives you an idea of where to look. Okay, so the next step is, so once again, if you're looking at this, the other way of looking at it is, I was talking about, you have these control points. Now along the normal, you can also look at intensity variations, right? In the training data, you can look at intensity variation. Okay, so this is again pixel intensity variation. Now I'm loosely using this 6 pixel intensity variation term. Ideally, you will have to take for every point. Okay, so you have a bunch of training data sets, right? Yes, in our case, and then you will have a bunch of these intensity profiles. Maybe all you can do is you can in fact construct some distribution from this, statistical distribution from this, like we did for the point cloud, for the active shape model, the shape model, and look where these things would match. Okay, So this is another way of doing it. Okay, so here in this particular approach, you can get rid of the dependence on the gradient. On top of this, you can also look at high gradients, and you can say, okay, once I hit high gradient, I also look at whether the pixel profiles there match. Okay, pixel intensity profiles there match at all. Okay, that's another way of looking of finding out Y's. Okay, so now we'll put this all together. Okay, putting this all together, okay, so estimate a statistical shape model using training data, okay, and the way to do that is to identify landmark points for the shape and annotate accordingly, and make sure that every shape you are annotating or every instance of the shape you are annotating in your training data set, you have the same number of points. Align all the shapes, removing, the what can I call scaling and post dependency, right? So that those two you have to remove. Okay, and perform PCA to obtain shape parameters. So now you have a bunch of points. There are just too many of them. You just reduce the size, the feature set, and to boil them down to a few parameters. B we call shape parameters, and we also have a bound on how much they can vary. Okay, so on the new image data, initialize a model with B equal to 0. So take the mean picture or one of the reference shapes that you had. And then put it on the image space, estimate Y, the target points by searching along the normal to the control points in the model. There are different ways of doing this, we saw that. And then you align X with Y by estimating scaling, rotation and translation transform. Apply this inverse transform, project to model space, estimate shape parameters, repeat this until convergence, especially the blue plots. Okay, this is how you would do this. Okay, so it's a kind of a complicated algorithm, but we put this in here because it's a natural continuation to what we have seen so far, right? So it's basically the active contour models, the geodesic active contours, and the level set based techniques, which all start from functional. They have some constraint on the curve that does the segmentation, right? Either you can embed the curve in a level set, or you can just work with the curve itself in the image space. But either way, there are some constraints on the curve, which are basically nothing regularization constraints, just to make sure that your curves are smooth, etc. Right? But there is no other constraint. Here, this has a shape constraint, and also there is a training data set concept introduced. So it will be a nice algorithm to know. Also, a very powerful algorithm used widely in its time. Even now, you can use it. There are now deep learning versions of this. If we get time, we'll cover that. Okay. Here are some examples. So this is for the knee in a MR picture right here. This is for the knee in MR picture. This is for space. So now you would this is your initialization, right? This is the shape that you have estimated, point cloud shape. You you have now initialized it close to the curve, close to where the actual segmentation has to happen. And then after 14 iterations, it kind of converges. You can see here. Similarly for the face, you have a model of the face given by the white curve. Put it on the face as close as possible, and then you can converge after 18 iterations. So there are quite a few freeware available for this, which you can download and play with, understand what it takes for this to converge. Okay, so it works in many situations, but it won't work when you have like very tortuous shapes. This is not a good algorithm to use. And also, if you're trying to segment a lot of small objects in a big picture and then label them, multiple instances of smaller objects, may not be a very powerful technique. Okay, you still need to get the target shape. Of course, that problem is solved, kind of by doing in a semi-automatic way, where you can just have somebody put the model shape very close to where it's supposed to be at, and maybe that part of the problem is slightly solved, but you still have to rely on some gradient information. Okay. So this concludes our session on the conventional image processing techniques. Next week onwards, we are going to look mostly at machine learning based techniques, specifically deep learning based techniques and 3D CNNs and generative models. Thank you.